Alright, let's begin from where we had left in the last video. As you could see here, we have arranged all the components that are required for this board. Now if I go ahead and turn on the rat nest, it will show all the connections that are required in order to complete the board. In fact, these are just lines. We need to draw tracks along with them, or we could complete the links to make the board completely routed. So also you could observe at the bottom that it says that there are 76 links and none of them are connected right now, and all of them need to be connected. So uh, this is how it is at this point in time. So before we proceed, I hope you remember what a mil is. So it is 1,000th of an inch. Usually uh, the track widths, the distance between pins of the component, which is also called pitch, and many other parameters with PCB design are still specified in mils. As well as if you change it into inches, you will see that the default track size is about 8 mils and the via is about 35 mils. So via, as we know, it's a connection from one layer to the other, or if there are multiple layers, it goes right through all the layers, so that you can route a wire from one layer to any of the other layers. Now the default track size is about 8 mils. uh, Now this is fine with most of the boards, but usually uh, when you calculate the current requirement for a board, so it depends on what type of application the PCB will be used in. So depending on the power requirement, you define the track size. So if you go back to the main KiCAD window and if you open up the PCB calculator, you will have a handy tool here in order to measure current that is required for the board. Now that is under track width. Now basically what it specifies is how much amount of current a track on a PCB can sustain. Now there are different factors which govern the current flow. Now if we imagine a track to be a 3D this thing, let's put up a sketch and see what are the things that will affect or govern the track width. Alright, so let's see the track widths in a little more detail. Now this is a very vast topic, and there are international printed circuit standards and a whole lot to learn. But what we'll try and do here is discuss the most important parameters and also look from a manufacturer's perspective as to uh, what makes a better design in terms of commercial value, as well as the parameters or design rules that need to be maintained. Now track widths, they play a very important role, and it is basically how much current a track is able to sustain uh, over a temperature rise, or so that is what basically we're trying to determine. Now if you look at the formula, it is derived from the IPC standard. So it says it eventually gives current as a result of the width that is required. But what you would usually need is the current that the board can sustain or board takes as an input from the power supply, and you need to determine what is the width required. And most of the times it is width, because let's see this with a small picture. Now see, imagine that this is a 3D view of our track. So let's see this. Now if you imagine that this to be the track length, if this is length, and if this is the copper thickness, and this is the width, what you could observe here is the copper thickness is usually very small and is determined by the fabrication process. So copper thickness, it it depends on the fabrication process. We'll see what the actual values will be, uh, and the length of the conductor, it basically is the length of the track between two adjacent components. So that is again determined by the spacing. So length is again uh, not of much concern. We usually have components closer to one another. So now the only parameter that remains to be seen is the width of the traces. Now this is in general for digital designs with not a lot of complications. So this is for fairly simple hobby designs, and even a few digital designs. Now let us see what determines this particular width of the track. If you look back to the formula here, so the width, it is like, say this is current, it gives current as an output. So width and all other parameters as well, they are directly proportional to the current that it sustains. So what it means is, the if the width is larger or the length is larger or the copper thickness is larger, it can sustain more current. So current will increase with increase in width or increase in the copper thickness. So, and as I said before, copper thickness is determined by the fabrication process. Now length depends on placement of the components, and width depends on the width is a factor that we are trying to find out. Now if you look at the calculator here, now these are kept at the default values, which is fairly which is a fair approximation for our project as well. The current usually it's about 500 milliamperes for such a design. Now if we look at the current, here we have 1 amperes, which is more than sufficient. Temperature rise is about 10 degrees, and the copper thickness, it is about 35 micrometers or 0.035 millimeters. Now this several manufacturers follow to be 70 micrometers and several at 35 micrometers. So let this keep at default as well. And conductor length is assumed to be 20 millimeters. The components are spaced 20 millimeters apart. Now if we see what is the minimum track width that is required, you would see that it is about 11.82 mils. So what is 11.82 mil mean? It means if the track if the track has to sustain a current of about 1 amperes, the minimum track width required for all the above parameters is 11.82 mils. So and now for our design, it's about 500 milliamperes or 0.5 amperes. So let's see that as well. So it comes down drastically to for about 4.5 mils. Now let us have these values just on the back of a mount on a mic. Let's see. Now when we get a board fabricated, the cost of it depends on, the first factor would be size, second would be complexity. Now, one of the things that is more important here is the complexity. So if the track widths are very less, say about less than 6 meals, then the cost would go up, the fabrication cost would go up. And again, if it is a multi-layer design, mm, the cost of the board goes up again. So what you could do is, and so what we have determined is the minimum width that is required. Now if you are able to make track widths more than what the minimum is, it's always better. And with the layers, the minimum layers you use, it's better. So usually these factors determine, and also one more factor that usually determines of how the PCB should be, whether it should be single layer or multi-layer, is the end application. Uh, so it depends on how much space you have for the board to fit in. So for hobby users, what we recommend is to make track widths as large as possible, and try to do boards in a single layer or a double layer for simple applications. So most of the times you will be done away with these things. Now what we usually follow is, we for the normal tracks, we track widths somewhere about 8 to 12 mils for all the digital lines, and about 25 mils for power. So this is what we usually follow. So what we had determined here was the required track width was about 4.5 mils, but we're using a track width between 8 to 12 mils for digital lines and 25 mils for power, which is significantly higher than the required ones, and which will not do any harm in artisans. Now having said that, what you could also observe here is, apart from the track widths, there is one more important parameter, which is uh, spacing or track spacing. So track spacing determines what is the space that is required to be maintained between tracks and between components. So so these are the two important parameters. One is the track width, and other is the spacing between tracks.